Programming the PLC. The most common way to program the PLC is to design the desired control circuit in the form of a relay logic ladder diagram, and then enter this ladder diagram into a programming terminal, which could be either a PC, a dedicated PLC programming terminal, or a special handheld switch box. The programming terminal is capable of converting the ladder diagram into a digital code and then sending this program to the PLC, where it is stored in memory. There are other ways to program a PLC besides ladder diagrams, and these will be introduced later in the module. There are currently many manufacturers of PLCs, and though they all have basic similarities, the details of the hardware and software will of course be different. The following discussion on programming will be kept as general as possible, but is patterned after the Allen Bradley line of PLCs. This seems a logical choice because Allen Bradley is one of the pioneers in the PLC field, and its products are respected and well used by industry. A PLC deals with two kinds of data that are maintained in memory: a program file in RAM or EEPROM, which contains the ladder logic program, and the data files in RAM, which hold the changing data from the control applications, such as switch settings. This table lists some of the more common types of data files. Input data, the current status of the externally connected switches. The output data, the status of those devices specified as outputs. Bit data, the scratch pad to store individual bits. Timer data, data associated with timers. Counter data, the data associated with counters. Control data, the data associated with sequencers and other devices. And integer data, numbers such as temperatures in binary form. Each data file occupies a portion of RAM memory and consists of any number of 8 or 16-bit words. This data arrangement is illustrated. The input and output data files are handled in a special way. The PLC automatically transfers the on-off condition of all input switches directly to the input data file in RAM as part of the scan. This is called making an input image table. Notice that a closed switch becomes a 1 in RAM and an open switch becomes a 0. Similarly, data in the output data file, called the output image table, are automatically transferred to the output module terminals. Thus, the PLC program actually deals with only the image data in the various data files. That is why each device on the ladder diagram, be it switch, relay, timer, or whatever, is identified by its address in RAM, even though the programmer may think of a certain switch as being, say, an overflow limit switch. The software thinks of it as being a particular bit in a particular data file. There is an important fundamental difference between a relay logic ladder diagram and a PLC ladder diagram. The relay ladder diagram is basically a wiring diagram, and a rung becomes active when current can flow from one power rail to the other. That is, if there is a path for the current through the contacts, then the load will be energized. On the other hand, the PLC ladder diagram is basically a logic diagram consisting of symbols, called input and output instructions, and a rung becomes continuous when there is a logical true path from rail to rail. If there is a continuous path of true input instructions from the left side of the rung, then the output instruction on the right side will become true. Therefore, writing a PLC program involves placing instructions in the rungs so as to obtain the desired result. Naturally, you can only use instructions that are supported by the language being used, but most PLCs support the basic components such as switches, relays, timers, counters, and sequencers. We will discuss each type of instruction next. Switches and relays are referred to as bit instructions because it only takes one bit to describe if a switch is open or closed. There are two kinds of switch instructions. One represents a normally open switch and the other a normally closed switch. Note that instructions and switches are different, but this helps introduce the concept. When the symbol is placed in the ladder diagram, it behaves as a normally open switch, push button, or set of relay contacts. It can be activated either by a real-world switch or another logical switch on the ladder diagram. In either case, when activated, the examine if closed instruction in the ladder diagram goes true. The state of the examine if closed instruction is maintained by a particular bit in memory, where a 0 means off, false, and a 1 means true. The address bit of this bit is placed on the ladder diagram next to the instruction symbol. When this symbol is placed in the ladder diagram, it behaves logically in the same way a normally closed switch does. That is, it is normally true and when activated goes false. It behaves like a logical inverter. Care must be taken when using this instruction in conjunction with a real-world normally closed switch, because it may not behave as you think. The problem is that people lose sight of the fact that a real-world normally closed switch and the examine if open instruction are not the same entity, but rather one drives the other. That is, the physical switch controls the state of the XIO instruction. Suppose you actually wired a normally closed switch to the PLC and used it to control an examine if open instruction. Then, if the real switch was activated, it would send a 0 to the PLC, and the logical XIO instruction would invert this false to a true, which may be backward from what you expected. To avoid this pitfall, remember that the real-world switch may drive the logical switch, but they are not the same thing. That is why you should use the terms examine if closed, shortened to XIC, for the normally open instruction, and examine if open, XIO, for the normally closed instruction. This symbol represents the relay coil, or simply the output signal. If there is a continuous true path through the rung, then the output will go true. Thus, if this symbol represents a relay coil, the relay will be energized. What really happens inside the PLC is that the bit in memory corresponding to this instruction goes to a 1. This bit may be used to drive an actual hardware relay through an output module, or to control an instruction in another rung, or both. In fact, there is no limit to the number of times this bit can be used by other instructions in the program, which is another advantage PLCs have over hardwired relay logic. The operation of the 3-bit instructions are summarized in this table. If the bit referred to for these instructions is a 0, then the examine if closed XIC instruction will be false, and the examine if open instruction will be true. If the bit referred to for these instructions is a 1, then the examine if closed instruction will be true, and the examine if open will be false. If the output is false, the bit associated with it will be a 0. If the output is true, the bit associated with it will be a 1. In a PLC ladder diagram, each symbol is accompanied by its RAM address, because this address tells the PLC where to find the present logical state of the symbol. Remember that the logical state of each symbol is always maintained in RAM. Titles of real-world components that the symbol represents, such as overload switch, are frequently added to improve clarity, but the PLC itself deals strictly with addresses. The address of an individual bit may be specified by 3 quantities: the file type, the word number, and position of the bit within the word. As previously stated, I/O signals usually have a direct relationship between the address and the physical connection point of an I/O module. For example, in the top rung, the address of flow switch is given as I:1/0. The I stands for input data file. The 1 means that the input module is plugged into slot 1 of the PLC chassis, and the 0 means that the switch is wired to terminal 0 of the module. The following is a more general interpretation of the flow switch instruction address. First letter is the type of data file, input in this case. The second character is the address of the word within the data file, or I/O module slot number. The third character is the bit position within the word, if appropriate, or the terminal number of the I/O module. The second examine if closed instruction of the first rung represents a switch wired to terminal 1 of the same input module used by flow switch. The output instruction activates terminal 3 of the output module plugged into slot 2. The operation of the top rung is as follows. The valve 1 output will go true when there is continuity through the rung. Continuity will be established when both examine if closed instructions are true. In other words, when the contacts of both flow switch and overload switch are closed. Operation of the second rung illustrates two important concepts. First, notice that the address of the examine if open instruction is the same as the output instruction in the top rung, meaning that the examine if open instruction will be controlled by the valve 1 bit located at address O:2/3. Secondly, because it is an examine if open instruction, it will go true only when valve 1 is false. So the warning light will come on when the valve goes off. The length of time delay is determined by specifying a preset value. Adam Bradley uses 10 milliseconds per count, so 500 represents 5 seconds. The timer is enabled when the rung conditions become true. Note that EN is true as long as the timer rung is true. Once enabled, the timer automatically counts up until its preset value, and then it goes true and stays true. The symbol for the timer instruction is a box, with the pertinent information placed in or about it, as shown and explained in the table. Notice that the timer instruction is placed in the rung. When switch I13 goes true, the timer starts counting. 5 seconds later, when the accumulator value reaches the preset value, the DN bit goes true. DN stands for done. Notice that the examine if closed XIC instruction in the second rung has the DN bit from timer 1 as its address. Therefore, it will go true after 5 seconds, causing the output instruction at O:24 to turn on a light. The timer shown is acting as an on-delay relay because it starts the delay when the rung goes true. Off-delay timers are also available. If switch I14 is opened, the timer switches off and EN and DN go false, and light O:24 switches off. A counter instruction keeps track of the number of times some event occurs. The count could represent the number of parts to be loaded into a box, or the number of times some operation is done in a day. Counters may be either count up or count down types. The counter instruction is placed in a rung and will increment or decrement every time the rung makes a false to true transition. The count is retained until a reset instruction with the same address as the counter is enabled. The counter has a preset value associated with it. When the count gets up to the preset value, the output goes true. This allows the program to initiate some action based on a certain count. For example, after 50 items are loaded in a box, a new box is moved into place. The symbol for the counter may be a box or a circle, a box for Adam Bradley, with all pertinent data placed in or about it. The ladder diagram is a simple circuit that counts the number of times the switch address I12 is opened and closed. The counter can be reset at any time by closing reset switch, because this action activates the reset instruction. The third rung uses the DN or done bit from the counter to turn on a light when the counter gets to 50 or higher. The accumulator holds the value of the count. And EN, like for the timer, is true when the counter rung is true. The counter address is used to identify the counter. The sequencer instruction is used when a repeating sequence of outputs is required, for example, a dishwasher that cycles through predetermined steps. Traditionally, electromechanical sequencers were used in this type of application, where a drum rotates slowly and the cams of the drum activate switches. The sequencer instruction allows the PLC to implement this common control strategy. This drawing shows the PLC sequencer instruction. Operation is as follows. The desired output bit pattern for each step are stored sequentially as words in memory. As usual, each bit in the word corresponds to a specific terminal of the output module. The output destination is defined in the destination address. Every time the sequencer instruction steps, it connects the next output pattern in memory to the designated output module. The address of the first pattern, the word, in the sequence is given to the sequencer instruction as the sequencer file address, which is address B1 in this example. The sequencer shown steps when the rung makes a false to true transition. Other versions of the sequence instruction allow the programmer to insert a time value for each step. The number of steps is defined in the length, in this case 4 steps, so the length is 4. All these functions are specific to the PLC you are working on, and as long as you know generally how they work, you can check the online help files when programming to ensure you are using them correctly. So far, we have just examined the basic instructions supported by virtually any PLC. PLCs are getting more sophisticated, and as they do, the instruction sets expand. In fact, many newer PLCs more closely resemble a real-time process-controlled computer than simply a substitute for relay logic. Many of the advanced instructions operate on a digital word instead of a single bit. Some of these words may be digitized analog data, such as temperature, used with an analog I/O module, which is an ADC or a DAC. Counter and timer accumulation values are stored as words. In many cases, the purpose of processing these number quantities is to arrive at a yes-no decision, where the actual output of the program is still in terms of individual bits, that is, turning a motor on or off. Then too, it is also possible to output a whole digital word to be converted to an analog voltage by an I/O module. Such a voltage could be used to control a motor's speed. The higher level instructions come in various categories. Comparison instructions compare two words and yield a single bit as a result. For example, a word may be tested to see if it is larger than another word, or to see if it is equal to another word. Math instructions perform mathematical operations on words in memory. These operations may include addition, subtraction, multiplication, division, and others. A math instruction might be used to multiply a sensor input word by a constant for scaling purposes. Logical and shift instructions perform logical operations such as and, or, and not, and right and left shifts on words stored in memory. For example, the AND instruction could be used to mask out certain bits in a word. Control instructions allow for such things as jumps and subroutines. For example, a jump instruction, when true, will cause the execution to jump ahead or back to any designated rung. PID control is available on some PLCs. In some cases, it is built into an I/O module. In other cases, it is programmed as an instruction in the ladder diagram. The PID instruction is covered in the next section. I/O messages and communications instructions allow the PLCs to send and receive messages and data to other PLCs or terminal PCs, for those applications where PLCs are networked together. PID control is becoming more commonly available on PLCs. In most cases, the PID function is implemented by an instruction and uses regular I/O analog channels. Another possibility is a separate PID hardware module, in which case it is actually an independent operating controller running under supervisory control of the PLC. The PID instruction implements the PID control strategy discussed previously in Module J. It would be used in a closed-loop system to control some physical parameter such as temperature, liquid level, or even motion, although a motion problem may require faster responses than the PLC can deliver. A sample PID instruction is shown in Figure B. It consists of a box with the pertinent information placed in or around it. It is usually on a rung or by itself. There is no condition logic on the left side of the rung, which means the PID instruction is always true. Thus, as long as the PLC is running, the PID function will be trying to maintain some physical parameter at its set point. The hardware to support the PID instruction is shown in Figure A and consists of one analog output channel for the output signal, CV, or the control variable, one analog input for the feedback signal, PV, the process variable, possibly an analog input channel for the set point, SP. However, the set point does not necessarily need physical input because it can be set by another instruction or simply by a constant. The instruction symbol specifies the addresses in RAM of the PID parameters. As shown in Figure B, these memory locations store at a minimum the current values of CV, PV, and SP, as well as the PID constants for the proportional, integral, and derivative, Kp, Ki prime, and Kd prime. Tuning the PID controller means finding the values of Kp, Ki, and Kd that cause the system to remain stable, respond quickly to disturbances without excessive overshoot, and have a minimum steady-state error. The method of tuning suggested by Adam Bradley is similar to the continuous cycle method discussed in Module J. This method is as follows. First, initially set Kp to 1, Ki to 0, and Kd to 0. Slowly increase gain Kp until the system goes into steady oscillation, and record the period of oscillation, period Tc. Initial settings: set Kp to half what was needed to go into oscillation, set Ki as 1 over Tc, and set Kd to Tc over 8. These will give you your initial values to start with, and then you can tune to suit after that. There are 5 languages that are all part of the IEC, the International Electrotechnical Commission Section 611313 standard. This IEC standard allows some ground rules that standardize PLCs and their languages. We have the ladder diagram, which you are familiar with. We have sequential function charts, SFCs, functional block diagrams, FBDs, structured text, ST, and instruction list, IL. In this course, we will mainly look at ladder diagrams and will cover the other PLC languages in ENGT 411 next semester. PLCs can be installed individually in standalone mode, or more often they can be connected to an industrial Ethernet network. This will be covered in more detail again in ENGT 411 next semester.